So let's talk about the second fundamental theorem of calculus. Now, I call it the second one because that's how I learned it and that's how the textbook that I'm teaching out of uses it. Some people actually refer to this as the first part of the fundamental theorem of calculus. As long as you know what it's talking about, though, the name of it doesn't really matter. So the other part of the fundamental theorem of calculus that we've talked about is using the antiderivative to actually evaluate a definite integral, right? That's the f of b minus f of a, right? If you're finding the integral from 1 to 2, it's the antiderivative of 2 minus the antiderivative evaluated at 1. So the second part of this fundamental theorem of calculus, the other part of it, is talking about these integrally defined functions. So a function that is defined by an integral, and how to take the derivative of those. So it's kind of marrying the two components of calculus. It's bringing together both derivatives and integrals into one problem. So what it says is if f of x is continuous, would really help if I could spell, continuous, sounding it out, on the closed interval from a to b, then capital F defined by capital F of x equals the integral from a to x of f of t dt, lowercase f of t dt, is also continuous. On the closed interval from a to b, and it's differentiable on the open interval from a to b, where capital F prime of x is equal to d dx of that definite integral from a to x of lowercase f of t dt, which is just going to equal lowercase f of x. Okay, whew, that was a lot. Let's break it down. Let's make this make sense. So capital F of x, and if you don't like using like capital F and lowercase f, just switch the capital F to be a G. Just make it another letter. It doesn't matter. Just typically we use capital letters for the antiderivatives, which is why we're using capital F of x here. So this capital F of x function is equal to a definite integral. So this is giving us our starting point. I'm going to zoom in here so I can write a little smaller. And then this gives us the variable that we're evaluating at. Now the weird part, so what this is really saying is if you want to find capital F of 2, you actually need to evaluate the definite integral from whatever your a value is to 2. So in other words, you need to find the area under the curve of this lowercase f of x function in order to actually find the uppercase f of x function's y-coordinate there. That sounds really confusing. We're going to make more sense of it. So the reason why there is an x at the top of the integral, but then there's this t here, and then this dt, is we call this a dummy variable. So it's just staying in place of the x, because you can't say that, like, you can't have two variables, like the same variable in two different spots, because the x at the top of the integral is telling you where to stop integrating at, whereas the variable that's inside the integrand is actually telling you just like what you're integrating over. I know that doesn't make a ton of sense, but it hopefully will once we start doing problems. So basically all this theorem says is that if you have an integrally defined function, so you have a function is equal to a definite integral, it's going to be continuous on the same interval that the integrand is, and you can take the derivative of that function, and all you do, right, so you're taking the derivative with respect to x, which is that variable at the top of your integral, and all you're going to do is replace the dummy variable here with the x. So let's make that make sense. So first, so eventually we're going to find f prime of x for all of these functions, but let's actually talk about how to evaluate some of these functions. So I'm going to actually throw an extra page in here real fast. We're just going to kind of go backwards. Okay. Just for some extra examples. So for example, say you have capital F of x is equal to the definite integral from -1 to x of 3x squared minus, we'll do plus 2x, oops, except these should be t's, plus 2t dt. Okay. So say, for instance, I wanted to find capital F of 2. So capital F of 2 is equal to the definite integral from -1 to 2 So that's going to give me t cubed plus t squared, evaluated from -1 to 2. So that's going to give me 8 plus 4 minus -1 plus 1. Okay, so that cancels out. So this is just 12. So capital F of 2 is equal to 12. Right, so if you just want to use an integrally defined function, you're just substituting in for whatever the limit, wherever the limit is, that's a variable on the integral. Then you're doing the definite integral and solving. You can also do these with graphs. So if they're made up of line segments and semicircles and stuff, you can find the area under the curves and add them all together and find your function value that way. So now let's actually jump back into what I wanted to talk about, which is how to take the derivatives. So we're going to find f prime, so capital F prime of x for the following functions. So if we're looking at A, capital F prime of x is going to equal to the derivative with respect to x of the integral from 2 to x secant of t dt. So the reason I picked this example is that you don't actually know what the integral of this function is, so you can't do it long way. You can't evaluate it and then take the take the derivative. So all we're going to say is, okay, the derivative of this is 1. So all I'm going to do is replace that dummy variable of t with x. And the reason I can do that, right, is because a derivative and an antiderivative, right, an integral, they're opposites. It's like pluses and minuses, multiplication and division. So whenever you see those two things next to each other, it's like e and natural log. Whenever those two things are right next to each other, they cancel each other out. So all we're going to do is put that variable down into the dummy variable spot. So f prime of x is just going to equal secant of x. And that's the answer. That's it. Okay, so let's look at the other one. It looks a little bit more complicated. It's actually not. So we have this funky looking integral in there, right? So capital F of x is equal to the integral from pi to x, right? Pi is just a constant, and you can use any constant you want there. And the integrand is e to the k times the square root of k plus k to the fifth, all divided by the natural log of k dk. So in this instance, I'm just using k as the dummy variable instead of t. You can use anything that's not an x. You can use anything that's different than the variable that's inside the function. Right, so if I want to find the derivative, right, if I'm being really good with my notation, I'm going to say, okay, it's the derivative of the integral from pi to x of this nasty looking thing. Right, and honestly, I don't know how to integrate this at all. I literally picked something that I don't know how to integrate either, so it's not like I'm trying to trick you or anything. Right, so these two things are opposites, so just like pluses and minuses, they're going to cancel each other out. So we're just going to move that variable down into the dummy variable spot. So our derivative, right, f prime of x is just equal to e to the x times x plus x to the fifth, all square rooted. Oh my god, my pen does not want to work. All over the natural log of x. And that's it. Now you might be thinking, okay, that's not too bad, but it's got to get harder than this, right? There's got to be another complexity level. And of course there is. So let's do that. So the only other ways that this really gets more complicated is there's two ways that the complexity can kind of get raised, right? If we have something other than just regular x at the top, or if we have variables in both locations. So we're going to actually kind of rely on some integral properties and some old derivative properties that maybe you haven't talked about in a while and you've kind of forgotten about. So let's look at the one on the left. Let's look at C first. So I have capital F of x, the antiderivative is equal to the integral from 0 to x squared of sine of t dt. So, right, in theory, you could absolutely find this function. right? You know how to integrate sine. You could integrate it, plug in your upper and lower bounds, and use your first fundamental theorem of calculus to find capital F of x, and then take the derivative. That seems like a lot of extra work for no reason. Okay, so if we write out the derivative of capital F of x is equal to the derivative with respect to x of 0 to x squared, integral of 0 to x squared of sine of t dt. Now, we have to be careful here because the derivative with respect to x of x squared is equal to 2x. So whenever we're taking the derivative, right, these two things are going to cancel each other out, but we have to take into effect that the x squared has a derivative. So when we go to find our capital F prime of x, we're still going to plug our upper limit in for the dummy variable, and then we're going to multiply by the derivative of the inside, right? You're just using chain rule here. So you can leave it like that, of course. I don't like writing it like that. I like to clean it up a little bit. So I'm going to say capital F prime of x is equal to 2x times sine of x squared. And that's the answer. So the only other way that these can get a little bit more complicated is if they have variables in both the lower and the upper bound location. So technically, if we look back at the definition of the second fundamental theorem of calculus, right, a is supposed to be a constant. The lower bound is supposed to be a constant. So technically what we're going to do is use some integral properties to break this up, and then you're going to see that you can probably use common sense to jump there faster. But we'll be good mathematicians and do it fully out first. Okay, so there's a property for definite integrals that says as long as there's a number in between them, right, you can just break them up. So I'm going to rewrite this function. I'm going to say, okay, this is going to be equal to sine of x to 0. It can be any constant you want. Legitimately doesn't matter. Of t cubed plus t dt. Actually, hang on. We're going to need more space than this. We'll just go to a fully new page. There we go. Okay, so maybe I'll do this one a couple of different ways and show you how you can jump to the formula, right, the final answer. But I'm going to do it with the definite integral properties first. So I'm going to break this definite integral up with a constant that's in the middle. Right, so I'm going to replace the upper bound in the first integral with 0, and then I'll make the same lower bound 0 in the second one, so that way they would add up to be the total area. Okay, now, the second fundamental theorem of calculus says that the upper bound should be where the variable is. So all I'm going to say is I need to switch my limits of integration for that first integral, so I'm going to throw a negative on it. Right, and I don't need to do anything to that second one. That looks like a delta or something. There we go. What is happening, Apple Pencil? Okay, we're spazzing, it's fine. Okay. Okay, now, I really don't like the fact that there's a negative in the front. That makes me a little uncomfortable. So I'm just going to flip the order of the problem, right? I'm just going to make it the integral from 0 to x cubed first of t cubed plus t dt minus the integral from, oops, and I suck because I was supposed to flip these limits. There we go. All better. That's okay. We all make mistakes. We fixed it. We caught it. It's fine. Okay. So, right. So now both of these integrals match the second fundamental theorem of calculus layout, right? There's a constant in the bottom, there's a variable expression in the top, so now we're going to go ahead, well, let's switch the color like I kind of wanted to, okay. Right, so now if I want to find capital F prime of x, I'm going to take the derivative with respect to x of both of these integrals. Right, so I'm just going to kind of distribute that d dx over both of them. right? So now if I follow along with my second fundamental theorem of calculus and what we saw in example C with the chain rule, right, I'm going to plug in my x cubed for my t's. And then I'm going to multiply it by the chain rule, right? So the derivative of x cubed is 3x squared. And then I'm going to subtract, I got sine cubed of x plus sine of x, all times the derivative of sine is cosine. And maybe we want to make this look a little bit nicer, simplify some exponents. I'm going to put the 3x squared out front. And then that's going to be x to the 9th plus x cubed, right? You could also multiply through, minus cosine of x times sine cubed of x plus sine of x. Right, so that would be our answer. So you might be thinking, do I have to break it up with those integral properties in order to take the second fundamental theorem? Absolutely not. Right, if you're looking at this and how the answer turned out, you're literally going to just use the first fundamental theorem of calculus. So if I copy this down, right, if you're good with this and once you feel a little bit more confident with your rules, right, method number 2, or maybe the faster way, right, my f prime of x is equal to d dx of the whole thing without breaking it up, right? And we're just going to bring that first part of the fundamental theorem of calculus into play. So I'm going to plug in, right? So remember when you do a definite integral, you evaluate it at the top minus evaluate it at the bottom. So I'm going to plug in with my x cubed again. And then multiply that by my chain rule. Minus plug in now with my lower bound. And then multiply by the chain rule, right? The derivative of the lower bound, right? So you can jump there a little faster. Another way you can do this, so let's do method 3 if you wanted to, if you're really struggling with this and you're like, I have no idea what to do. If it's something that you can integrate. Right? I know how to integrate that. That is 1/4 times t to the 4th plus 1/2 t squared. And I want to evaluate that from sine of x to x cubed. Okay. So I can actually find what this capital F of x function is. I can absolutely do that. That is 1/4. So x cubed to the 4th. We'll show all the steps here. Plus 1/2 times x cubed squared minus 1/4 of sine to the 4th of x plus 1/2 sine squared of x, right? And if we simplify that, we get 1/4 x to the 12th plus 1/2 x to the 6th minus 1/4 sine to the 4th of x plus, minus, because I would distribute the minus sign, sine squared of x. So now if I wanted to take the derivative of that, right, it's just normal derivative rules. Okay, so I'd bring down the 12. 12 over 4 is 3x to the 11th. Bring down the 6, I get 3x to the 5th. So hang on, right? If I were to distribute this through, right, I would get 3x to the 11th plus 3x to the 5th. Oh, okay, checks out. Minus, bring down the 4. The 1/4 is going to cancel out. So I'm going to get sine cubed of x times the derivative of sine is cosine of x, minus the 1/2 and the 2 power will cancel out when I bring that down, so I'm going to get sine of x left, times the derivative of sine of x, which, oh hey, right, that's just sine cubed plus sine, all times negative cosine, that checks out, right? So you can get the same thing if you actually go ahead and find the capital F of x function, but that only works if you know how to integrate.